Hey everyone, my name is Lisa and I'm here to talk to you today about our Kotlin journey at Instagram. So before I share more, just a little background about me. I've been with Instagram or Meta for about 2.5 years. I joined Instagram as an Android engineer on our mobile infrastructure team. The team has gone through several rebrandings and iterations, but the mission has always been the same. Today we're called the Instagram Developer Craft Team, and our mission is to empower Instagram product teams to ship code fast and reliably. So our team works on anything that can benefit the developer experience, and this ranges from just core infrastructure APIs to even developer tooling. Kotlin was first put on our radar in 2018, and that might seem a little late to the game, especially for those of you who have been writing Android code for a while. But migrating a codebase of our size from Java to Kotlin was pretty challenging simply due to the scale of our codebase. So the Instagram Android codebase is about 8 million lines of code, and we have around 250 Android engineers. Instagram exists in the same repository as many other apps in the Meta family, and these apps include iOS apps, server apps, and other Android apps. To give you an idea of that scale, in our monorepo, we have over 100 Android apps alone. This Android code accounts for 33 million lines of code within the monorepo, and we have about 1,500 Android engineers across Meta. So a large infrastructure change like migrating Instagram to Kotlin involves a lot of coordination with teams outside of Instagram across Meta. And just because of the scale of our monorepo, we had a lot of challenges on this path to Kotlin that I'll get more into later. So now that I've sort of set the tone for the scale of Android development at Meta, let's talk some more about just our typical Android workflow. So we use Buck as our build tool. Many apps out there use Gradle. Today, they're a lot more similar than they used to be, but historically, we built Buck in-house at Meta to combat the build speed problem with that much code at the company. So as you can imagine, in a code base of our size, build speeds becomes increasingly important to developer productivity. The last thing you want to do is hit build to build and install the app to test a feature, and then you have to wait 20 to 25 minutes just to be able to see the app on your device. Android Studio is our IDE. We have built a lot of custom plugins and tooling on top of Android Studio, so the experience is a little special at Meta. And as I described earlier, we exist in a monorepo with most other Android apps at the company. Now, historically, the language of choice for Android development was Java, but I'm here to talk to you today about how that became Kotlin. So to back up, a little bit of what we're talking about today. So first, we'll talk about why Instagram chose to invest in Kotlin, and then we'll talk about the path to adoption. We'll wrap up with a little bit more about the future of our Kotlin investment at Meta and what the future holds. So as we discussed earlier, making the decision to shift from Java to Kotlin was a pretty huge undertaking, and that's mostly because of the size of just Android development at the company. So what makes Kotlin worth the investment? Kotlin was equally an app reliability play and a developer experience play. Null pointer exceptions are the #1 cause of user crashes at Instagram. Java is not a null-safe language. Kotlin is a null-safe language, so it forces you to handle nullability thoughtfully. Less user crashes obviously means a better experience for our users, but also less developer time spent on null safety bugs and sevs. Furthermore, Kotlin has a lot of syntactic sugar that makes writing code intuitive and concise. Kotlin has a better functional programming style support and language features like smartcasts, coroutines, extension functions, just to name a few, all of which make code simpler and more robust. JetBrains also benchmarks that the same program written in Java versus Kotlin, the Kotlin version will have about 40% fewer lines of code. Less code means easier diff reviews, less to maintain over time, and less legacy code that just becomes tribal knowledge in the future. App reliability and developer experience are very compelling reasons to invest in Kotlin, but a third reason is pretty simple. our developers just wanted it. So these are a couple quotes from Instagram product engineers using Kotlin, and they attest to how much people love writing Kotlin code and how people feel empowered to write code quicker and more reliably. So we made a big bet at Instagram that Kotlin was the future of Android development across the industry. And this meant that perhaps in the future, modern development would maybe be blocked on using Kotlin. This was a little bit of a bet, but it's been pretty true. Declarative UI, for example, is unblocked by adopting Kotlin. Many of you might be familiar with declarative UI, frameworks like Jetpack Compose or Swift UI. These are gaining popularity across the mobile development industry. Declarative UI just simply allows you to declaratively write UI elements in only Kotlin versus the legacy APIs that involved writing both Java code and XML. Instagram has increasingly been looking at Jetpack Compose as the future for our UI development, and Compose is written for Kotlin development. Compose is another developer productivity play. So this new style of UI programming also results in fewer lines of code, and the syntax is a lot clearer, which means that UI code is easier to maintain and write over time. As Kotlin gained popularity in the industry and frameworks like Compose started popping up, it became more and more clear that modern Android APIs are built for Kotlin. And it almost became indisputable that not migrating to Kotlin almost put Instagram at Meta at risk long term. So once we found alignment in why we were investing in Kotlin, we got to work on Kotlin adoption throughout the Instagram codebase. So our journey really begins in 2019, and this is the point at which we first started investing in addressing infrastructure blockers that were blocking simply compiling Kotlin code within the monorepo. So this work involved working with our Buck team to ship Kotlin support for Buck, and we also partnered with a few select product teams just to sort of pilot what does it feel like to write Kotlin code at Instagram. By the end of 2019, we had about 7,000 lines of Kotlin code in the Instagram codebase. From there, we had the confidence to widen the net of people writing Kotlin code at the company. And in 2020, we focused mainly on, instead of just enablement, how could we improve the developer experience of Kotlin so that it was at parity with the experience of writing Java code. So a lot of our focus at this time was in our continuous integration pipelines, shipping lint support, basically just closing the gap between developer experience writing Java versus Kotlin. In 2021, we announced that Kotlin was an open adoption. So this meant that any team could freely write Kotlin code at Instagram, and all of our infrastructure improvements at this time really focused around performance. So, for example, a really big project at the beginning of 2021 was working with our Redux team to improve app size for production builds using Kotlin. Many of you might be familiar with Redux. It's just an Android bytecode optimizer to make app size smaller for production builds. It kind of obfuscates like method names, things like that, to just make the binary smaller. And we didn't want any difference between Java and Kotlin at this time. So by the end of 2021, we announced that Instagram was Kotlin first. Now this means that we expected all new code to be written in Kotlin. So these two graphs kind of paint the picture of how Kotlin adoption progressed at the company. Both graphs start at January of 2021 and end at September of 2023. We've got percent lines of code on the left, and we've got the number of Buck targets with Kotlin code on the right. So today we're at 63% lines of code in Kotlin at Instagram, which is really exciting. And this is basically tripled from January of 2021, which was around 20%. Earlier in 2023, we surpassed the really exciting milestone of half the code base being written in Kotlin, so 50% lines of code, which was very exciting. Once we enabled Kotlin adoption, growth was pretty healthy and organic. Like I said, people love writing Kotlin code. This was not, however, without a pretty large speed bump. So as Kotlin grew in our code base, our build speeds regressed dramatically. So in 2022, this was around the time we hit 30 to 40% lines of code in Kotlin. we were collecting signal that our Android build speeds had more than doubled, so they regressed by over 100%. As I sort of mentioned earlier, with the code base of our scale, build speeds are always top of mind. It's a major hit to developer productivity if you have to sit there and wait for a build. So this is bad. But why was this happening? What makes Kotlin so much more expensive than Java? So for one, the Java compiler is just more mature, and therefore it's just faster than the Kotlin compiler. People have been iterating on it, making optimizations on it for years. And so from a throughput speed perspective, Java is just going to be faster for now. Buck support for Java is also a lot more mature than support for Kotlin. So remember, we built Buck in-house at Meta some time ago, and the team has been iterating on Buck feature sets with a Java in mind. And Kotlin was something, completely new that was just put on the map in 2019. Additionally, earlier we talked about all of the reasons we love Kotlin, all of that syntactic sugar like extension functions, data classes. All of that stuff is really nice from a developer experience standpoint, but it comes at a cost when it comes to the compiler. The compiler is going to be a little bit slower when handling some of those language features, which is more prevalent in Kotlin versus Java. So we've got 3 graphs here that are sort of explaining the cost of building Kotlin code. On the y-axis for each graph, we've got time spent compiling. And on the x-axis for each graph, we've just got % lines of code. Now, let me draw your attention to the leftmost graph, our most simple graph. This is just showing you that the more lines of code of Kotlin you have, the slower your builds. Easy enough. So the graphs in the middle and on the right take it a step further by taking a look at the critical path. For those of you unfamiliar with build systems or compilers, basically a critical path is just the longest path in your build graph that the compiler has to compile. And we've got this legend here with a few different critical path lengths. In yellow, we've got the shortest length, which is 1, and the teal line, we've got the longest length, which is about 145. And then the other colors are just, some options in between. So the graph in the middle, we have incremental builds where the ABI has changed. ABI just stands for Application Binary Interface. I'm going to explain that a little bit more on the next slide. But you can kind of think of the middle graph as showing us that the compiler needs to recompile code because something has changed, versus the rightmost graph that doesn't need any recompiling. But as you can see, the longer your critical path, the more dramatic this build speed cost becomes when compiling Kotlin code. So cue in Kasabi. So Kasabi is a set of compiler plugins built for Kotlin in-house by Meta. Kasabi generates source-only ABI jars. Let's back up a little bit. We talked about ABI, Application Binary Interfaces. So basically, when you build any sort of JVM program, your output is a jar file. And a jar file is essentially a zip file that represents all of the JVM code and metadata in your application. So with Buck, every Buck target produces a sources jar file. Sources jar files contain all of the code that's in that Buck target. Additionally, Buck will output an ABI jar. And the ABI jar is all of the public-facing code in that target. So you can kind of think of it like the public API of that target. Now, obviously, that's going to be less code than you've got everything in your sources jar, and you've got just your public-facing stuff in your ABI jar. So those ABI jars are smaller, and the compiler can load them into memory faster. So an optimization that build tools make is using ABI jars rather than sources jars when compiling the application. So there's a couple different kinds of ABI jars. We've got source-only ABI, which is what Kasabi generates, that's on the left, and we've got class-only ABI on the right. Class-only ABI, which is what we were working with before Kasabi, the way that we generate this ABI is we compile the whole target, so all of the public stuff, all of the private stuff, and then we go back in a second step and we strip out all of the private stuff. The way you generate source only is a little bit smarter. It doesn't have to compile the whole target to be produced. It uses some heuristics to make inferences about things that typically you would only know if you compiled the whole target, but it works a little bit smarter, and so you don't have to put it simply. So this means that you have more parallelization and you reduce the number of cache fetches. So let me take your attention to source-only ABI on the left, and you can see that it's a lot shorter than class-only ABI on the right. Now, this is the same build graph. And you can see that there's more options for parallelization if you're just looking at it from like a past perspective on the graph. So this is why Kosabi is like a stepwise improvement for build speeds for Android. So these two graphs describe Kosabi's impact on Kotlin build speeds. So again, we have percent lines of code in Kotlin on the x-axis and time spent compiling on the y-axis. The graph on the left is for all critical paths of 171, and then the graph on the right is a critical path of 137, so it's a bit shorter. The blue line on both graphs has the least amount of source-only ABI and the most amount of class-only ABI. The purple line for both graphs is the greatest amount of source-only ABI. Builds are not deterministic, which is why there's some variability for the different amounts of source-only ABI for both critical path depths. But in general, you can see the purple line generally compiles faster, and that's the line that has the most source-only ABI. So this is basically telling us Kosabi makes Kotlin build speeds faster. In summer of 2022, Instagram was the first Android app at Meta to integrate Kosabi. Now this made sense because Instagram had the most lines of Kotlin code at this time, and so it was just a natural choice to pilot this new source-only ABI generation tool. These two charts show you sort of the adoption story for Kosabi, which we elected to do incrementally just so that the team could address any bugs or issues that came up throughout the integration. So on the left, we have all of the build steps for a target. The orange part is just Kotlin, and then the purple part is Kosabi. So as you can see in summer of 2022, the amount of Kotlin goes down, the amount of Kosabi integration goes up. And that graph is just zoomed in on the right, where Kotlin is in blue and Kosabi is in green. So by the end of 2022, about 86% of all Kotlin targets had Kosabi enabled. So adoption went smoothly. How did we see this develop in our build speed problem? So this graph has a lot of information, but take your attention to the baby blue area. That area shows you time spent compiling Kotlin code. The other stuff is compiling other sorts of things, other build steps in the process. Just focus on the baby blue part. We've got time on the x-axis and time spent compiling on the y-axis. On the x-axis, we start in H2 of 2022, I believe. And at this time, it took about, on average, 20-something seconds to compile Kotlin code. Over time, as we started integrating Kosabi and source-only ABI into more and more bug targets, that area shrinks. And toward the end of H2 2022, it took about 10.8 seconds to compile Kotlin code on average. So this was about a 55% reduction in time spent compiling Kotlin code and a 38% reduction in time spent compiling Android code overall. So this was a huge success. At this time, we were also increasing Kotlin adoption. So that means that we were combating making the build speed problem worse, and we were also fixing the build speed problem by converting existing modules to Kosabi. So our work with Kotlin at Meta is definitely not done. There's still a lot of investments we need to make. Particularly, null pointer exceptions are still a big issue. Despite the fact that Instagram is over 50% Kotlin by now, we've still got some work to do, and we're doubling down on Kotlin to solve these problems. In 2023, Instagram is moving on from simply Kotlin first to now Kotlin everywhere. And so this means that our focus is not only writing new code in Kotlin, but we're aggressively migrating existing Java code to Kotlin. One of the ways that we're doing this is with the Kotlinator code mod service, which is built in-house at Meta. Now, if you're unfamiliar with a code mod service, I think I might have touched on this with Kasabi. It also used a code mod service for enablement. But this is basically just an automated way to put up pull requests that developers simply have to approve and ship. So we have some code that we wrote that modifies code with a script, publishes a diff, and then you just accept it and ship it, which is pretty cool. So Kotlinator uses the J2K tool, which some of you might be familiar with. This is the tool that JetBrains developed that basically in Android Studio, when you see that little button that says migrate this Java file to Kotlin, that uses the J2K tool. So Meta built on top of this tool with some pre-processing and post-processing steps to build Kotlinator. These pre- and post-processing steps just try to address some nullability concerns because one of the biggest issues we've seen with rapid Kotlin adoption at the company is nullability. We're working with a foundation of Java code that is not null safe, and we're converting that to something that enforces strict nullability. So a lot of issues that have lingered around and we've kind of gotten away with Java rise to the surface once we convert some of that code to Kotlin. The team is investing a lot into making these Kotlin conversions as safe as possible and eliminating our nullability concerns as we continue to migrate. K2 is the new Kotlin compiler from JetBrains, and they've benchmarked about a 55% improvement in compiler throughput speed. Earlier, we talked about source-only ABI and incremental builds. K2 is just simply faster than the previous version of the compiler, which is really exciting. We're one of the first large code bases at Instagram to adopt K2, and we spent 2023 basically migrating all of our Kotlin compiler plugins to K2 APIs. This has been a little bit challenging because those APIs are still experimental. We're kind of, soon to the game here. So things change with each Kotlin version bump, and the team will have to go back and address any breaking changes from updating the Kotlin version. The APIs are also not well documented at this point in time because they're still experimental. So we've been partnering with JetBrains to solve, different bugs that pop up and maybe ideate helpful APIs going forward. And we look forward to continuing this investment through the rest of 2023. As we look to 2024, Kotlin continues to be a major focus for the team, and we're committed to making Instagram Kotlin everywhere. We are really excited to continue the Kotlin journey at Instagram. It's improved the lives of our developers, it's unblocked modern frameworks, and overall has improved app reliability for our users. If you enjoyed today's conversation, be sure to check out my blog post on the @Scale website. Thanks for listening.